2, 1. So one example that we want to be able to do and take the derivative of. So it's the end of the calculus side for you. And your teacher gives you this example and asks you, all right, so can you take the derivative? Can you find the derivative of this function? Well, as you will see, you're going to have to utilize every single derivative rule that you had. You have constants here, you have power function, you have sinusoidal function, you have logarithmic functions, you have an exponential function. So all of these different parent functions that you have, so there's an enormous composite function made up of many components. And it also has the product rule, the quotient rule, okay, the additive, okay, rule, so the summation, okay, of two functions. And with that, it means that we're going to have to do quite a bit of work. So I would encourage you, pause the video, and then try to see if you can find out what the derivative of this is. Then you can replay the video and see, all right, did I get it right or wrong? So let us kind of get started in here. I don't know how long this is going to take and how much space I'm going to need, but I'm going to give it a shot. Okay, so if I take this, I'm going to break this down into kind of few components in here. So I do notice that I have a product, right? So I have this. I'm going to treat this as one of my functions in here. And then I'm going to treat this, okay, as the other function. So I'm going to make this a product, okay, of these two particular functions. Now, of course, I'm going to have to dive in there as well to find the derivative. So if I'm going to take the product of these two, the first one, so the 3x squared that I have, that 3, in reality, I can just take it out entirely. But I'm going to just keep it as 3x squared just in general. So what I'm going to do is I'm going to have the product of 3x squared, which is going to be 6x. So that is the derivative of this. Now it's going to be times, okay, the product of that entire big item there. So that is going to be cos of log of x plus pi, assuming that it's in radians there, divided by e to the x. And now I'm going to take the addition, so now it's the addition of, now again, the 3x squared, and now I need the derivative, okay, of that entire junk. So I'm going to say derivative, and I'm going to call this, all right, let's call this some function g of x, okay, so that entire green item. So I need to take the derivative of this entire thing, dx. Okay, so let's brace ourselves. So now the derivative of this, so I'm going to rewrite it, g of x equals all of this right there. I'm going to duplicate it, bring it down. So that's my g of x. And now for this one, once again, I'm going to break this down for us. So I'm going to break it down in the following way. So I'm going to break it down so that I have a quotient rule in here. So I'm going to take this as one function, and I'm going to take this as my other function right here. So now I need the quotient rule to be applied to this g of x. Okay, so with the quotient rule, what does that mean? I'm going to take that cos, so take the derivative of this, and that's going to be, I guess, negative sine of all of that junk that I will have right there. Now I need to multiply it by the derivative of inside of here. So this is going to be multiplied by whatever the derivative is of that. Now I have log of x, right? Okay, so that is, I guess, base 10. So that's going to be a tricky one in there. Now, luckily, the pi is just a constant, so there's nothing to worry about there. So that entire thing is going to be 1 all over ln of 10 multiplied by 1 over x. It's the derivative of the interior there. So that is just that first green item that you see on top. And all of this is going to be multiplied by e to the x. So that's what we would have right there. Now that's just the first component, because what we need to do is we need to split it up. So now this is going to be, because of the quotient rule, so now I'm going to have to take subtract, and now I will have to rewrite it. So this is going to be cos of log x plus pi times, and this is going to be times, now the derivative of e to the x. Luckily, it's also e to the x, so I will have that. And now all of this is going to have to be divided by, so that's going to be division by e to the x squared. So that's going to be e to the x. Now I have to square this. Now, of course, okay, you can rewrite that as just simply e to the 2x, okay, if you wanted to. And that is giving me, here is my numerator, okay, of the quotient rule. And then in the bottom is my denominator, and it is squared. So I have now taken the derivative, okay, of the entire thing. And what's interesting here is that I clearly would have had to fit that all over here. So all of that, so the derivative, so this, okay, is what you see right there. So that is the derivative of my g, okay, of x. So that would have gotten all the way over here to get my full derivative. And as you can see, it's extremely long. So it starts with all of these. So it was 6x times all of this, that's coming from the product rule between 3x squared, times the derivative of all of this, and that derivative you see right there. Now, all of this is definitely doable. You should be capable of doing this, and I wonder if you actually pause the video and force yourself, okay, to see if you can work this whole thing out. Now, one thing that we cannot forget, the domain for this, if I go back to the original, there's actually not much issues in the original function. The 3x squared, it's defined for all of x. So e to the x is actually defined for all x. Okay, so if you recall, e to the x is just an exponential growth. Okay, that's in the denominator, so it's never 0, so that's not a problem. Cos of anything is never a problem. So the only thing that we have a problem with is this log of x. And as you know, for log of x, we need to have x to be greater than 0. So that would have been our restriction on the function. So this is defined for x is greater than 0. That's our function there. And for our derivative, if you're going through and you're looking, okay, for example, through that, again, so 6x, so as we're kind of peeking in here, so as we would be walking ourselves one by one through this, no issues there. Actually, we would have no issues over here with the e to the x. So again, we only have a problem with the log x. So that still restricts it for x is greater than 0. There's no additional restrictions there. And then the derivative, so sine is fine. Okay, the cos is fine. The only problem that we would run into is over here, 1 over x, but we already know that x is greater than 0. So that is the only restriction that we would have. So this is going to be definable for everything. So our derivative exists for x is greater than 0. That's what you would actually have in here. Now, to finish all that off, let's plot it up on Desmos. Okay, so to take a look, so this is what we would have. So I plotted the actual function. Okay, so it does look like a nice, kind of a neat function right there. And notice that it is actually defined everywhere, except we run a problem at 0 and it's not defined, okay, on the left of 0, so on the negatives. And it is a pretty nice function, actually. It's pretty well behaved. Now, we can take this, I can define it through as our final result. So let's say call this fx equals, and then that way, if I call maybe g, or let's say maybe f, okay, this would be the derivative of f. I used the g in my other one, so maybe let's call it h, is equal to f at x. There is your derivative. As crazy as it looks, okay, that is your derivative function in there. And we can plug in what we have found over here. So if I would take this out, let me split it up in here. So if I take that entire thing, okay, so notice that f prime of x, which is the derivative, Desmos does it for us, we can also substitute this entire thing to check if those actually derivatives align, if we did it correctly in there. So I'm going to do that in fast forward fashion. I'm going to enter it all into Desmos, and let's see, okay, if they're going to be on top of each other. So let me be right back with this. All right, so welcome back. Okay, so I entered the whole thing in there. I called it m, so meaning the derivative is called m at x. Okay, just kind of running out of variables here. Okay, so for calling our function, so this is my 6x and so on, 3x squared times, and then this is my the actual derivative of that g of x. I called it n of x. Okay, so that's a derivative, and you see that at the bottom there. Okay, so it's quite of a pain to try to enter it in, but there you have it. So that's the entire derivative. And so Desmos, as you can see there, f prime of x gives us the derivative. And so if I click this on, notice that it overlaps exactly. So our derivative was correct. All right, so it was a lot of fun, okay, to do this example. I hope that you got it right. It really tests all the basic rules that you have in one function of all the derivatives, and also forces us to think about the restriction on the domain. Thanks for watching. Okay, hopefully we'll see you in future videos. Take care, everybody. Bye-bye.